Good morning all together. Welcome to our August session of Let's Talk Science. Once again, we will touch an interesting topic all around IoT this morning. Today, our session will deal with artificial intelligence. It's of great importance that AI models in production can adapt to the variations of the process. For example, tool wear, they must be dynamic. Mr. Marcel Wichmann will illustrate a new approach to solve this problem and present 3 use cases where he has tested it and shows that it is working. Mr. Marcel Wichmann is research assistant and group leader at the Institute of Production Engineering and Machine Tools of the Leibniz University in Hanover, and he and his team are working and specialized on planning of manufacturing processes in production systems. So I'm looking forward to hear these interesting aspects, and I am handing over to Marcel Wichmann. Afterwards, you may put your questions and comments into the chat so that we can see it, and then we will have the possibility to just discuss it together. So, Mr. Wichmann, the floor is yours.
Yeah, thank you, Dr. Schäfer, for the kind introduction. So hello, also from my side. Today, I want to present the topic AI is finally becoming widely usable to you. And I want to answer additionally the question, how digital twins help to use AI in process chains. But let me first start with a short introduction. So I want to talk here about the global air traffic. This is a picture with about the global air traffic in the year 2013. And beside these, a lot of flights which are shown here, we have the topic of manufacturing of aircrafts. And when we have a look to that topic, then we have 2 things here. First, the manufacturing, and secondly, the maintenance, which have to be economically and sustainable in the long term. So the topic is manufacturing and maintenance of aircraft components. This is the agenda of my presentation. I want to talk about the manufacturing process chains in the aircraft industry. I want to talk about AI-based self-learning process adaptation. That's my approach, which I want to show you today. And then we will see the 3 use cases. And in the end, I want to summarize and show you manufacturing process chains of the future. So, manufacturing process chains in the aircraft industry. I have shown here 2 process chains which are important for our investigations at our institute. So in the picture at the top, you can see the process chain of the production of cutting tools, typically out of cemented carbide. And we are starting here with the tool grinding process. So you can see on the left side a reference workpiece with helical flutes in it. And after the tool grinding process, we have a quality assurance. Then the tool is used in a milling process, for example, or also in a drilling process. You can see here also this arrow, which is now going from using the tool from the top to the bottom into the second process chain. And there we have the process chain of milling aircraft components, or also of repairing aircraft components. Yeah, when we going ahead, you can see the quality assurance after that. And when the tool was used, we can also recycle this tool and bring it back in our manufacturing to use the tool. So this is the process chains on which we have a look today. And now I will come to my approach first, and I want to show you how AI models can be used in a self-learning process adaptation in these process chains. So first, I want to start with a vision of an autonomous production system So in a typically production system, you have a lot of data. So you have the value stream itself, you have the products, the components, you have cutting tools, you have the processes, and the production systems contain a wide range of useful data, but the use of this data is not merged today or currently, and it would enable an intelligent production. So merging all this data is important to form an autonomous production system. How can we do that? So the problem on which we are looking here is that manufacturing data is not merged today. Knowledge remains at experienced staff, and assistance systems in process planning are rigid. They cannot adapt to other circumstances. And the objective here is to combine different data types, to use simulation-based process adaptation, and to realize a knowledge transfer to save resources. So in the end, we have the approach of an AI-based self-learning process adaptation, in which we are also using digital twins. Here I show you the approach in a picture. So typically our processes will start with the chem planning. So after the design of a new product, we have the computer aided manufacturing, and after that NC code is generated to run our machine tools. We are using in our approach not directly the process. We are using first the NC simulation. This is a material removal simulation, which enables us to calculate the local cutting conditions between the milling tool and the workpiece, for example. Local cutting conditions are indicators for learning models, and by using these learning models, we can do predictions to adapt our initial process planning. And this adaptation is starting before the first real process to have a virtual adaptation and optimization of our processes. In the end, we're having optimized NC code, as you can see on this blue color. And then we are starting with the process. And I've talked before a lot about different data which is not merged. So here you can see 3 data streams which we now want to merge. The process itself is running, and thereby we can using parallel to the process data. For example, out of the machine control, spindle current or axis currents. Additionally, sensor data, for example, is also a thing which can be used here. And then we are using the axis data of our machine tool to run a process parallel simulation. So that's an additional simulation, which can be also named as a kind of a digital twin, which is using the axis position to have a process parallel simulation to generate simulation data. This is also our cutting conditions here. And in the end, we have the quality assurance, and also the quality assurance, there's the quality data, which is resulting. And all these 3 data streams are merged together in a knowledge database. And this is really important to train the learning models and to adapt also the models. By using this data feedback, we are getting much more better models with a lot of production data. As you can see, in the end, we have our workpiece A, and then it's possible to have a knowledge transfer to the next workpiece. So please imagine you have a new workpiece B in red here, and that we wanted to produce here. That's here a drilling tool, for example. And by using our approach, we can have this knowledge transfer. So here you can see also these 3 data streams again. And then I want to come to my 3 use cases in which I want to show you that approach, and in which I want to show you also digital twins or process parallel simulations, which are used here. So let me first start with a digital twin in tool grinding. So tool grinding is typically here shown. So here we have a helical fluid grinded workpiece, but the process itself can be seen here very well. So the grinding wheel is going through the workpiece, and typically we have additionally cooling fluid, and that's the process itself. When we have a look to our digital twin in tool grinding, then you can see here on the left side the real manufacturing, the real machine tool, and the grinding wheel, and also the workpiece and the resulting workpiece. For example, here after helical fluid grinding. On the right side, you see the material removal simulation. And these both worlds are now combined by using data streams. First, our axis positions to run a process parallel simulation. And also you can see here the 3 data streams: process data, quality data, and simulation data. And all these data streams are going together in a knowledge database. I think the idea here is to use this local cutting conditions, which you can see here. And the data can be saved by using the cutting conditions generally. So when we have a new tool, maybe similar cutting conditions are resulting also by grinding a new tool, and thereby a knowledge transfer is possible. So in this video, you can see the process parallel simulation. So the tool grinding machine is running. It can be seen better when we are coming to the second fluid after the first, and the simulation runs by using the real axis data. So also when we will change, for example, here the feed rate directly at the machine tool, our simulation will show the same behavior as the reality. And my topic on this slide, it's a little bit full, so I will explain it step by step, is how can this data be used now in AI-based models, or how can AI-based models be used to adapt the process or to make the process better. So please have a look first on the right side here on this picture. So I will activate the laser pointer now. We are starting here with our typically NC code, and then we are having before a new process optimization algorithm. So we are using automatically controlled Dexel material removal simulation, and our AI model here, it's a support vector machine model. Support vector machine is a supervised based machine learning method. By using that, we are predicting our results. For example, the quality of the workpiece. And then we have objective function to have a look to the result. Is it good or is it bad? And criterion. And when the criterion is fulfilled, we're going to our grinding process. If the criterion is not fulfilled, we are going over to our optimization algorithm. And this optimization algorithm will then adapt our process parameters. For example, the algorithm will then adapt the feed rate or also the cutting speed. And this circle is running a lot of times iteratively to optimize our process parameters. And in the end, we are having, by using the AI-based models, optimized process by using also our knowledge database. So process adaptation can be realized virtually. And in the end, we are realizing also a self-learning system by using data feedback. Here it can be seen how the data are going into this feedback loop. So we are having here our database again. So the simulation data is going in the database, and also the quality data and the process data. And then we have our ML modeling process step. We have also evaluation of the ML model, and then our model here is updated. So this is really important to see how these data can be used after our process optimization to make the AI-based models better in the end. Yeah, and here a few results are shown. I think here you can see a lot of them. That's why I want to focus on two examples. So first, please have a look to this red box now. Here we have a process parameter optimization regarding the workpiece quality. So you can see here first the quality regarding to the roughness, the surface roughness. Then you can see the quality regarding to the shape error. So it's here the core diameter deviation. And then you can see the productivity by looking to the process time. And we adapt here the process parameters. So you can see here in the end our feed rate and our cutting speed, which was adapted by having the objective to make our quality better. And the blue bar show every time our initial values, and the gray bar our values after optimization. You can see here very well that we are reducing our surface roughness by 47%. We are reducing our shape error by 47%, our surface roughness by 31%, but we are increasing our process time by 112%. The second example is shown here. Here in the blue box, we adapt our process regarding to the productivity. So as you can see, process time is going down. So we're having a faster process, but our shape error is going up. Our process parameter optimization has, in this case, also the goal to optimize also our surface roughness in the end. And here it can be seen that it's possible to have the same surface roughness, but a faster process, for example. So these are our first results to show you how can these AI-based models also be used. But regarding to my presentation time, I now want to come to the next use case first to show you more examples. Here we are looking to the repair process of fan blades. So it's the recontouring of fan blades. After a grinding tool is grinded and can be used, we are having a look here to use the tool in our repairing process. So here you can see a turbine maintenance repair, and the typically process is that we have a fan blade and we are having maybe a patch on it, or also a weld seam on it to add a material after or in the maintenance repair. And in the end, this added material must be milled again to generate the targeted fan blade. So here we have an individual cam planning, and you can see here by looking to this extrapolated area, to the new area which must be added and which must be generated again in this maintenance process. Here you can see also the ball end mill, which is going around the blade and using here the tool blade. So our approach here is to research and develop a software which are using CAM methods for virtual process planning. It's really difficult because every fan blade has a geometry and shape error which is very specific. So every fan blade repair must be planned here individually. So also in this case, we are using digital twin for generating relevant data. For example, here you can see the welding process to add new material to our product, which will be repaired. So here you can see the welding process, and then axis positions are used to run also our process parallel simulation, which can be seen here on our right side. So in the end, we are realizing thereby also a digital twin. And the important thing is that we want to generate thereby the local geometry of our weld seam, which can be then used in process planning. Also here we have models. For example, there's the question, how high or how wide is our weld seam in this simulation? So the axis positions can be used directly from the machine. But the question is, how is the weld seam looking in the end? And here's additionally a second use case, for example, for AI-based models in the future. We are using also a data feedback to generate these models, and they are using the current I and the feed rate to predict our weld seam height and our weld seam width. Also in this case, it's really important to have such prediction models. So I think on this slide, a lot of information is shown. I want to go a little bit faster through it by just telling you the important things. So really interesting is here that we can have an adaptive tool path planning for our individual repair case. So first, our specific fan blade is scanned and we have the geometry. After using this geometry, we can reconstruct our initial geometry and have a prediction for that. Then the target geometry is identified and we are doing our tool path planning for the recontouring, which can be seen here on the left side. Here, our digital twin from the welding process is again really important because we can use this digital twin here to simulate by the planned tool path with the real welded workpiece, and thereby we can also calculate our local cutting conditions in the simulation. And thereby it's possible to calculate in which case we have more material or less material, and in which case also our tool path planning here must be adapted. So a very specific, difficult process planning here, but it can be optimized by using this intelligent planning methods and also by using our digital twin to have a better look to that. And here you can see again a video of our simulation of the recontouring process. And you can imagine when we are using in these simulations, then our digital twin of the welding process, it can be better simulated in which cases we have more material movement, in which cases less, for example. And in the end, you can see here the real recontouring process in which it is very important to have an optimized toolpath planning. So now I will come to my last use case. In this use case, I want to show you digital twin in quality assurance. So after generating or grinding a cutting tool, after using this cutting tool in repair processes, here we have a look to our quality assurance, maybe after repairing a component, or also in the case of the new manufacturing of a component. Here on the left, you can see a reference workpiece out of our investigations. So the topic here is the inspection planning. So typically quality control or quality assurance has to be planned also, and the economic planning is really important to ensure a good quality, but also to do it economically. It's a one-time execution of this work planning is extremely time-consuming and cost-intensive, and that's why we want to have a look to a better, intelligent inspection planning. The challenges here are that a low availability of production data is currently there. So we want to synchronize also here significant machine, sensor, and simulation data to realize a virtual quality inspection. So feedback knowledge from quality inspection to inspection planning is important here. targeted planning of quality inspections to avoid unnecessary inspection efforts. And in the image on the right side here, you can see this approach. So we have our initial inspection plan, and again here our milling process and the real access data is used to run a cutting simulation. We have the cutting conditions, we have a digital footprint, and our AI-based quality models predict the quality which can be saved in our digital twin. And this is important here to adapt our inspection planning. So please imagine when our digital twin can show us by these predictions on which positions it's more important to have a focused or a lot of more inspection, then that would be save resources, because other aspects don't have to be focused so much. And in the end, we have an adapted inspection planning and a better quality assurance. So that's our approach. Also here, we have a similar picture like in the two cases before. So our digital twin for virtual quality inspection on the left side, the real manufacturing, on the right side, the material removal simulation or the digital twin. And again, here, like in the first use case, the access positions are used, process data is used, quality data and simulation data, and all these data is merged here in this case in a quality database. And first, I will show you a video of this digital twin again, so that you can imagine how this will be looking. So here we have a reference process with a star geometry, but it can be seen very well also for a 5-axis process in this case, how such a process parallel simulation can be run and how the simulation will generate important data for the local cutting conditions. So that can be seen here now. So here this local cutting conditions are visualized. For example, here's the material removal rate. Yeah, and here also the local depth of cut and so on. But as I said before, how in this case can this data be used to generate AI-based models and to make the process predictions also better? Here we have investigated 2 workpiece geometries. So on the left side, workpiece 1, on the right side, workpiece 2. And here you can see a result for having AI-based models. So we're using here again a support vector machine with training data set of 70 workpieces. We are modeling the shape error in ball end milling based on simulated local cutting conditions. The important thing here is that we are using in both prediction cases, so also for workpiece geometry 1 and for workpiece geometry 2, just the data of geometry 1. So that can be seen here. So trains with data set from workpiece geometry 1. And also we predict by using this model the shape error in the aspect of workpiece 2. And in both cases, it's possible to predict the deviation. It can be seen here. So here we have the measured deviations and the simulated deviations. And the perfect case will be when each point will be on this line directly. But you can see in both cases, it can be predicted very well how our shape deviation is. So thereby, we can show that a sufficient model quality can be achieved for kinematically more demanding use case, the small training data sets, and it's possible to transfer knowledge to other workpiece geometries. That can be demonstrated thereby. Yeah, so after going through this three use cases and to show you things about our process adaptations, how can AI-based models be used, and also how can digital twin be used for data merging. I will come in the end to my last slide to the summary. And the summary in the summary, I will show you the manufacturing process chains of the future. So again, we have the manufacturing process chains of my first slide, but now we are adding digital twins to that. So in tool grinding, for example, you have our digital process twin, the quality assurance after the tool grinding generate a digital workpiece twin. And also here, by using the tool, we have a workpiece twin. The recycling process itself can be also realized by using a digital process twin. Yeah, below we have our milling process, which is shown before. And now you can see that in the future, we want to transfer the workpiece twin after the tool grinding to our digital process twin of the milling process here. And in the end, we have our quality assurance, and there we are using also the workpiece twin. So a lot of twins are coming into our production system, but this is really important to generate more data, to save data, and also to use in the end, thereby AI-based models. And what is really important here to show that our twins will be influenced by the reality and also influence the reality itself in a feedback. So that is an important aspect when we will have a look to twins. In our case, the processes were adapted by our predictions, and thereby the twins and the predictions will influence also the real world. So that's my last point. Digital twins are able to predict and optimize processes by using artificial intelligence. So thank you for your attention, and feel free to ask questions.
Well, thank you, Mr. Wichmann. This was very interesting. That I think that there are a lot of future use cases that can be optimized by such a system. Some questions came up. So first question is looking into the grinding process, which is a complex process as such. All the three topics are working together real time, right?
Yes, I will go to the slide again. It's maybe better to show it. Yeah.
But are there, if you look into even other, you may look into other processes, are there time constraints depending on the complexity of the process, the tool, the simulation, which give you problems to install such a AI driven optimization?
Yeah, so maybe we have to separate that. So it's not really important to have these AI-based predictions parallel to the process. So for us, it's more important to save all these data parallel to the process. And in our approach, we want to make future processes better. So adapt the planning of, for example, the next batch size, which will be manufactured. Okay. And thereby, we don't have this time problem for the adaptations of the next process. But the simulations can be run also for faster processes parallel by having a not so detailed resolution. But in the end, that will be also making our quality more bad. But I think when we have a look to our approach that we want to make the planning for the next batch size better, then it's not a big problem with the time.
Mm-hmm. With your last use case, you mentioned that you initially had 70 data sets to start the AI. So is this a number which is more or less what you need to have a first simulation or first results, or is it depending on the various processes?
Yeah, interesting question. It's depending on the various processes, but in manufacturing we have in a lot of cases, so when we are looking to specific work pieces in small batch sizes, the problem that we are having not so many data sets. And AI is typically, or AI methods typically must have a lot of data to be good. For example, this image processing, which you all know by using neural networks, there a lot of data sets will be used, to 10,000 or 100,000, for example. The question is, how can we use AI also in that cases with not so many data sets? And we have in our investigations seen that, for example, methods like the support vector machine can be used better for smaller data sets. And we have also other investigations in which we are using neural networks, but in these cases, a lot of more data have to be there. And that's why in this case, we are using a support vector machine.
Well, this question came up with your second use case, where for these repair processes, it's more or less a one-piece process. So can you learn such a model out of more or less similar other repair processes in this area, so that over the time you can optimize it?
Yeah. I think what really is important is the idea of our local cutting conditions. So, for example, when we are having in this simulation here also predictions for the shape error or predictions for the material removal itself, then it's important that we have here not just one value at a time step. So we have a lot of values. So when you imagine that our cutting tool can be discretized, like the grinding tool, which I've showed before, it's possible to calculate for each single cutting condition a prediction. And maybe in the next fan blade case, so in the next repairing case, the geometry itself, it's another, but we can find similar cutting conditions in it, and thereby it's possible to transfer it.
Okay. Well, I think this has been all the questions. Thank you, Mr. Wichmann. I think it's a very interesting and also important topic for the future of production, as you have already mentioned. And I wish you all the best for your future research work. And to our people listening, in our September session, we will continue with the topic of artificial intelligence. Professor Metternich and Mr. Jordan will focus on the implementation of AI models. So be with us on the 28th of September, same time, same location. And I wish you all the best and have a nice day. Bye-bye.